Welcome to tutorial number 3. In this tutorial we're going to be discussing basic units of electricity and conductors and insulators. Later on in this tutorial I'll be going through some multiple choice questions and answers with you, and these questions and answers are very similar to the types of questions you could get in the standard amateur radio theory assessment. In your document folder, the doc folder on your CD, you will find a Word document and a PDF document called sample questions. It's far more beneficial if you print this document. It's fairly large, it's 80 pages, but it's broken up into sections, and shortly I'll be going through section number 1, which is only about 2 or 3 pages, with you, and marking and explaining the correct answers to the multiple choice questions. So it's a pretty good idea if you print that file, and again it's called samplequestions.doc or sample questions PDF. You don't have to print it all at once, but I will be going through that entire document with you in these tutorials. Good idea to have a hard copy sitting next to you so you can write on it and make comments. The electrons in conductors are not tightly bound to the nucleus of the atom. If we were able to look inside a piece of copper, not connected to anything, just sitting on the table, we would find that the electrons are moving around due to the heat energy in the conductor. Room temperature, from a galactic point of view, on Earth is quite hot. So a copper conductor sitting on a table, or anything made of copper, will have free electrons that are not bound tightly to the nucleus, wandering around in that copper wire. All metals are the same. All metals are good conductors. A really good indicator as to whether something is a good conductor or not is whether it conducts heat. If a material is a good conductor of heat, then it is most likely a good conductor as well. The electrons in insulators are not free to move around. They are tightly bound or connected to the nucleus, and even if we apply an external force such as a voltage and electrical pressure, we may not get any of those electrons to move at all in a good insulator. On screen I've got a list of conductors and insulators. I'll scroll down so you can see all the insulators shortly, and I thought I'd highlight the ones that you really need to be aware of for assessment purposes. Probably the best conductor in the conductors list would be gold. Gold is an extremely good conductor. It's not used as a conductor because it's so expensive. What is used is other conductors are plated with gold to reduce their resistance or increase their conductivity. So it's not uncommon to find the contacts of relays gold plated. Some circuit boards actually have their tracks gold plated. And another very good example is a resonant cavity used by radio amateurs on repeaters, which is basically a high Q tuned circuit. The inside of the cavity is usually plated in a very good cavity with either gold or silver. Silver is the next best conductor on this list compared to gold, and it's a little bit cheaper than gold. The conductor that radio amateurs deal with the most, or the two conductors that radio amateurs deal with the most, are copper and aluminium. Copper is cheap, and it's also a very good conductor for the wiring within a radio or the copper tracks on a circuit board. However, in spite of copper being a very good conductor, aluminium would be the most common conductor used in the world. Aluminium is nowhere near as good a conductor as silver, copper or gold. However, it's cheaper, it's corrosion resistant, it's not very ductile compared to silver, copper and gold, and that means it doesn't stretch so much. So aluminium finds applications in the power industry. Most of the power lines, it's lightweight as well. Most of the power lines are made from aluminium conductors. Telephone cables are made from aluminium conductors. And radio amateurs use aluminium as a conductor for their antennas because it's cheap, it's light, and it's rigid. It's the most abundantly used conductor of any other conductor there is. Just have a quick look down the list. There are a few others. If you can remember that all metals are good conductors. There's a couple of things on the list that are not metals because other materials conduct besides metal. There's graphite, and graphite is also carbon. Carbon is found in batteries. Some plastics also have carbon or graphite in them. Now this is a bit dangerous because plastic we normally assume is an insulator. If a plastic has got a lot of carbon in it, it may well conduct. So be careful with screwdriver handles that are made of plastic that are not meant to be used on high voltages, because you might be surprised and find out that the plastic you're using will conduct a little, enough to give you a shock or an awful fright. Dirty water is a conductor, concrete is a conductor, mercury, bronze, brass, steel, iron, aluminium, gold, copper and silver. If you can remember carbon, graphite, silver, copper, gold and aluminium, you'll do well with any of those questions on the assessment. Just scrolling down to look at the insulators. Glass is a very good insulator. It's used on power poles. The large insulators on power poles are often made of glass. Rubber, of course. Rubber mats on a workbench or under an electrical workbench is a good idea. Oil, asphalt, fiberglass to a lesser extent, but it is a fairly good insulator. Porcelain and ceramics make very, very good insulators, very good high voltage insulators. Quartz, cotton, paper, wood, notice they've got to be dry to be an insulator. So if you're going to pull someone off an electric cable because they're having a shock, don't grab hold of a piece of wet wood because you'll end up in as much trouble yourself. Plastic, and again the caution there is be careful with plastic. Some plastics are not rated to withstand high voltages. It's most important when you're buying screwdrivers and pliers and things like that, that you may, and sometimes there is no choice, but you have to do something live, adjust something in a radio while it's on and there's a high voltage present. You should use the appropriate high voltage screwdrivers. Air is a good conductor. It takes about 10,000 volts to arc across 1 centimetre of air. That's a rough rule of thumb. That's dry air. It takes about 10,000 volts to arc across 1 centimetre. If the air is humid, got water in it, it will arc at a shorter distance than 1 centimetre. Diamond, pretty expensive insulator diamond. Pure water is also an insulator. I've got some examples of conductors and insulators on the screen. By far, the most common conductor that you're actually going to see is going to be copper, if you ignore power lines and telephone cables. But the wiring in your transceivers is going to be basically copper. And on the left we have a large roll of copper wire. On the right here we've got a copper cable which has several conductors in it, and the conductors have plastic insulation around them, and a sheath also made of insulating material. The sheath, by the way, on cables is normally treated for insects and rats. So some cables will be eaten away quickly, particularly by mice and rats, but other cables have a very, very hardened jacket which makes them insect and pest resistant to some extent. I'll just scroll down a little bit. On the left we've got some insulators made of ceramic. They could just as easily be made of glass, and these insulators look like, to me, they come from the power industry. So a very, very long insulator like that would withstand a very, very high voltage, and the smaller ones they'd withstand a much lower voltage. But all of these insulators would withstand thousands and thousands of volts. On the right hand side we've got an egg insulator, and you can see the dimensions there. It's about 3 inches long. Egg insulators are used by radio amateurs to tie their guy wires and sometimes their antennas, to tie their antennas off, because you don't want the wire of the antenna just connected to a branch of a tree. So you would have an egg insulator, connect the wire antenna to that, and then the other side of the egg insulator you connect to the tree either via a wire or using a nylon rope, something like that. There's an example of the use of an egg insulator. In this case it looks like it's holding stainless steel wire, but a radio amateur would do the same thing. He would connect his antenna wire to one side of the insulator, and whatever was holding the antenna up, whether it be wire or nylon cord, he would connect the other side of the egg insulator to the anchoring point for the antenna. Just in passing, I might go back to the conductor list again for a second, if I can find it. Forgive me. Here we are. There's our conductor list. I'll just do a page down there. I often get asked from radio amateurs and students of amateur radio which is the best conductor to use for antennas, and most radio amateurs tend to use copper wire, which can be rather expensive. However, what I use is, more often than not, I use galvanized iron wire. I use it, it's not as good a conductor, but the difference between using galvanized iron wire for your wire antennas and copper wire is imperceptible. I use galvanized iron wire because it's cheap, it's tough, it's hard to see. You can pick up 40 meters of wire for around about $10 or $12, and it's very, very good for wire antennas. You've just got to be careful you don't kink it. If you don't kink it, it won't break, and it's fencing wire. It's designed to last for a very long time, and I'm a bit of a cheapskate. If galvanized iron works and I don't know the difference between copper wire, I will certainly use galvanized iron wire as I do for my antennas. But some people look a bit strangely at me when I do that. Just while we're here, there is another group of materials that are neither conductors nor insulators. Those materials are called semiconductors. They're neither a good conductor nor a good insulator. They could just as easily have been called semi-insulators, because they're part way between conductors and insulators. And semiconductors are very important in radio. And the two materials that you do need to know which are semiconductors are silicon and germanium. There are other semiconductors, but they are the most common ones. And we'll be doing a lot more on semiconductors in this course later on. On screen I've brought up a graphic or picture of an electric buzzer just to illustrate the different uses of conductors and insulators. Let me just explain first how this buzzer works. We have a battery, and that battery consists of 4 cells, and to me they look like AA batteries. Sorry, AA cells. And when you have a group of cells, 4 in this case, you call it a battery. You have a battery, and you've got a red and black wire coming from the battery. The black lead is negative, and the red lead is positive. Now, electrons don't run out of the battery and move around the circuit because there are electrons already in the circuit. There are electrons in this black wire now. There are electrons already there. In all of the conductors, this is a bolt with a nut on the end, and it's got enameled wire wrapped around it. Enameled wire is copper wire generally with a special enamel insulation around the wire. So even though that wire looks like it's bare copper wire and they should all be shorting out to each other, in fact all of that wire around the bolt is an insulator. The base upon which the buzzer is made is also an insulator. When a wire carries an electric current, a magnetic field is created around that wire. So if you were to wind the wire into a coil, you would actually get a bigger magnetic field passing an electric current through a coil of wire. To make that magnetic field even stronger, you can put a material inside the coil of wire which concentrates magnetic lines of force. And soft iron does that very well, and the bolt is made from iron. So we've stuck an iron into a bolt of iron, soft iron, into a coil of wire, and what we've created there is an electromagnet. So when a current flows through this magnet, both ends of the bolt become very strongly magnetized with a north and a south pole. When that happens, this armature here, this moving metal vane, is pulled inwards to the metal bolt, and that breaks the circuit. The circuit is this wire here going underneath the armature to this screw, and that screw is just touching that movable armature. Let's have a look at how current would flow through this circuit. Electrons would leave the negative terminal of the battery, and they would travel this way through the wire to the armature. And remember, that bolt is touching the armature, so that electrons travel to the adjusting bolt, then through this wire, through the electromagnet. So the electromagnet is going to become a magnet, out of the electromagnet, along this wire. This is a spring, and you can push that down with your finger. If that's pushed down with your finger, it makes contact with this black wire underneath, so you've got a complete circuit. So that's a switch, in fact. So you could send Morse code on this if you want to do. And the current will then flow back to the positive terminal of the battery. So if your finger's down on that, making a circuit, we've got a complete circuit. Every time the electromagnet becomes magnetized, it pulls this armature in towards the head of the bolt. When it does that, it opens the circuit. The screw here is not movable, so when this armature moves inwards, it actually breaks the circuit and turns the current off. When the current is turned off, the electromagnet is no longer a magnet and the armature springs back to the spring, and of course that makes the circuit again, and the electromagnet is again switched on. So in effect, this armature just buzzes. It's a buzzer. And if we wanted to, we could extend the armature and put a little bell here, and instead of having this sort of armature, we could extend it with a little ball on it, and that ball could ring a bell, and then we would have a bell. But the way it's set up at the moment, it's just a buzzer, and it's turned on and off by pressing this strip of metal here, which is a homemade switch, or a homemade Morse code key, if you like, because you could send Morse code on this. So that's a really good example of where different conductors and insulators are used. In the battery, if it was a Leclanche cell, the center of the battery would be a carbon rod. That's a conductor. The can that the battery is made in, or the cells are made in, could be made of zinc if it was a Leclanche cell. There are different types of cells, and cells normally get their names from the types of metals that are used in them. It would be called a carbon zinc battery, but the original name for it was a Leclanche cell. While we're talking about magnetic fields produced around the electromagnet, there is a question you may be asked about magnetic fields and how to shield them. If you want to shield a magnetic field from affecting things nearby, and we have coils of wire, inductors we call them in radios, and they have magnetic fields around them, and if those magnetic fields are allowed to go out and stray too far away, they can actually make electrons move in adjacent components in the radio, and that would cause a real problem. So there is a need to be able to block or shield a magnetic field, and what is used generally is soft iron. I'll just scroll down. This is a horseshoe magnet that I've drawn. Bit of a rough sketch, I know. I'm not the greatest drawer. And you can see the magnetic field emanating from it between the north and the south pole. If we want to contain that magnetic field so that it doesn't radiate out like that, and we certainly do inside transceivers, we would need to put a piece of soft iron between the north and the south pole, and that's called a keeper. And all it is a little piece of soft iron. You could actually use a bolt to do the same job. We don't use horseshoe magnets in radios, but we do use coils of wire. Let's say this electromagnet or this inductor was in a transceiver. You would have to shield it from affecting other components in the transceiver, and the way you would do that is you would put a soft iron box shield over the magnet. That's why when you open a transceiver, you'll see all of these usually chrome little metal boxes. They are covering inductors, and they're covering those inductors, coils of wire, to prevent their magnetic fields from interfering with other parts of the radio circuit. While I've got this up, I'm just going to trace out the circuit again for you because it's a rather useful model, this. The circuit for the electrons is from the negative terminal. We'll presume the switch is closed, so electrons are going to flow, and that is just a connecting nut, to the armature. Current flows along the armature to the adjusting spring. That spring can be adjusted to in and out to change the speed at which the buzzer buzzes. Then electrons travel to the electromagnet, through the electromagnetic coil, through the electromagnet's coil, out of the electromagnet here, along the spring of the switch, through the black wire, and back to the positive terminal of the battery. Electrons always flow from negative to positive. It's a negative that's got the excess electrons, and the positive which has the deficiency of electrons. What I wanted to mention is how fast do you think the electricity flows around such a circuit like this? In actual fact, the electrons travel very, very slow. In fact, it may take an hour for an electron here, if we left the buzzer going for an hour, it may take that long for that particular electron to travel all through this circuit, because there are so many electrons in these wires that they all move very, very slowly. The effect of electricity at a distance is instant, because the things that make up electricity, electrons moving, are already in the circuit. The electrons are already in the magnet. The electrons are already in the switch, in the interconnecting wires, in the armature. The electrons are everywhere. And when we connect the battery, we create an electrical pressure which moves them ever so slowly. They move very, very slow. In most cases, slower than walking speed. Now for a little bit on electrical units. We'll be talking a lot about electrical units, so don't get worried about these too much for now. In the next tutorial, I think it is, we'll be discussing Ohm's law in much more detail. What we want to achieve right now is just an understanding of, a very basic understanding of volts, amperes, ohms and watts. And you'll get a deeper understanding in coming tutorials. The unit of electrical pressure is I just might try and highlight for you. The unit of electrical pressure is the volt. Another name for voltage is electromotive force, or EMF, and the symbol used in radio for voltage is E. We don't use V. Electrical engineers use V, and that's because they don't use V for velocity. In radio we use V for velocity, so we use E for voltage. Voltage is known by other names, and I think I'll type them in because you really do need to know them. So voltage is electrical pressure. That's the name I prefer. Voltage is electrical pressure because it is voltage that pushes electrons through a circuit. The more voltage you have, the more electrons you have running through the circuit. It's part of Ohm's law. In fact, if you double the pressure, you would double the amount of electrons. Now, the electrons running around the circuit is the current measured in amperes. But let's finish with voltage. Another name for voltage is EMF, written above, electromotive force. Another name would be potential difference. All of those are terms that could be used for voltage. Electrical pressure. The ampere is the unit of electrical current. That's how many electrons are flowing. It takes a lot of electrons to make 1 ampere. If you were to measure the water going into being pumped by a pump, you would measure the flow of water in perhaps litres per second. In electricity, the flow is the current measured in amperes. The letter we use is I, and an ampere is 6.25 by 10 to the power 18 electrons per second past a given point. I'll write that down for you. 6.25 you don't need to know this for assessment, by 10 to the power 18 electrons. Now I'll just superscript that. Oh, I made a subscript out of it. How did I do that? Subscript, that's what we want. Okay, 16 by 10 to the power 18 electrons. So if you really wanted to know how many electrons per second is 1 ampere. So if you really wanted to know how many electrons that was, you'd type 6.25 and the 10 to the 18, I'll just fix up my formatting, the 10 to the 18 means you have to move the decimal place 18 places to the right. So there's the decimal place. Let's move it 1 place to the right, 2 places to the right, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And we'll take the decimal point out now. So that's how many electrons need to be flowing past a given point in the circuit in 1 second for there to be 1 ampere. And that many electrons is given a name. It's called a coulomb. So we could define 1 ampere as 1 coulomb per second. So ampere is the flow of electric current through a circuit that is pushed by the voltage. The circuit has resistance. All conductors have some resistance, and the unit of resistance is the ohm. And when we write down say 100 ohms, we use the omega symbol, or sometimes we just write 100R as well. But when we use resistance in equations, we always use R. So for voltage we use E in equations, for amperes we use I in equations, for resistance we use R in equations. The unit of electrical power, or how much heat or work is being done by an electric circuit, that's what power is the watt. Let's see if I can highlight that, is the watt. We use P in equations for the watt. So how much power is being used by a circuit is measured in watts, and watts is simply the product, the multiplication, the product of the current in the circuit multiplied by the voltage in the circuit. So power in watts equals the current in amperes multiplied by the voltage in volts. Or put just a little bit more simply, P equals E multiplied by I. Sometimes when two letters are written beside each other without a multiply sign, it means they are multiplied together. So we could have just as easily written P equals EI, E by I. So if you know the voltage and you know the current, you know the power in watts. If you had 10 volts and 10 amps, then 10 times 10 would give you 100 watts. Now, if you know any two of voltage, current and resistance, you can calculate the other two. And a really handy way of remembering the three equations for Ohm's law, that doesn't include the power equation, P equals E times I, is the Ohm's law triangle. Now with the Ohm's law triangle, you simply put your finger over the one that you want. So if we're looking for current, we put our finger over the I, and we get I equals E over R. I equals E over R. That means E divided by R. So I equals E divided by R. And of course that answer is going to be in amperes. Oops. Just might carriage down a bit. If we wanted to find out, of course E is volts, I is amperes, R is ohms. If we wanted to find the formula for R, and you will have a formula sheet in your assessment, but you still need to be able to identify the formula you need to use and then still know how to use it on the calculator. But we'll be helping you with that. It's not hard. If we wanted to know the formula for E, we would write down E equals, and we would put our finger over the E, and then we'd read the other two. E equals I, R, which means I multiplied by R. So if we want E and we know I and R, we simply say E equals I multiplied by R, and of course our answer is going to be in volts. If we want to know R, we simply put our finger over the R and read the other two. R equals E over I. R equals E divided by I. R equals E divided by I. And of course that answer is going to be in ohms. That's the Ohm's law triangle. We'll visit this again, and we're going to be going into Ohm's law a lot more deeper and showing you just how voltage, current and resistance and wattage interacts with each other. It's now time to go through some of the multiple choice questions of a type that you could get during your standard amateur radio assessment. These multiple choice questions are just on basic units, conductors and insulators. You can print these questions from your document folder. The file is called samplequestions.doc. I'll just highlight that for you. You don't have to print the whole document at once. It's 80 pages. You can print a section at a time as I'm going through it with you, so that you can sit there and make marks and notations on the hard copy. That will help you a great deal. Let's see how we go. Question 1.1. The material best suited to shield a circuit from a permanent magnetic field is... Well, remember we were talking about the buzzer and the coil of wire and how we would have to shield that magnetic field from other components inside a transceiver, and the material we use for that is soft iron. It has to be a magnetic material, and soft iron is a magnetic material. None of the others are magnetic. Aluminium is not magnetic. Lead and copper are not attracted to a magnet. You need a material that makes it easy for magnetic lines of force to flow through to shield a magnetic field, and such a material is soft iron. The unit of electric current, I think you should have that by now. The unit of electric current is the ampere. The farad is the unit of capacitance. We'll be talking about that later. The watt is the unit of power, and the volt is the unit of electrical pressure. Question 1.3. Electromotive force, EMF, is measured. Well, EMF, electromotive force, is just another name for voltage or electrical pressure. So EMF is measured in volts. (1.4) The unit of potential difference. Potential difference is just another name for electrical pressure, which is measured in volts. The unit of electrical power, remember P equals E by I. P equals E multiplied by I. So if you had, let's say you had 10 volts and 1 amp. So 10 volts, we'll make it 10 volts and 2 amps. 10 volts and 2 amps would give us 20 watts. So the unit is of power is the watt. The best conductor, 1.6, the best conductor of electricity on the following list is, well, silver's pretty good. Iron's not as good as silver. Germanium is a semiconductor. It's neither a good conductor or a good insulator. And don't forget that the other semiconductor is silicon. You need to know both of those. But certainly the best conductor on that list is glass. Oh, sorry. Best conductor is silver, not glass. Silly boy. So silver is a better conductor of all of those. Copper is a better conductor than iron. Aluminium is a better conductor than iron. But the other two, germanium and glass, one's a semiconductor and glass is an extremely good insulator. Question 1.7. Which of the following is the best insulator? Well, carbon's not an insulator. There's a carbon right in a battery. It's a conductor. Zinc is a metal, so it's not an insulator. Gold is a metal, so it's not an insulator. But one of the very best insulators we have, particularly for making high voltage insulators for power lines, is the ceramic insulator. Last one, only a very short section this one. 1.8, a semiconductor conducts better than an insulator. Well, a semiconductor is halfway between a conductor and an insulator, so it would conduct better than an insulator. Let's have a look at the other ones and see if why they're wrong. Conducts half as well as a conductor. Well, that's just nonsense because we don't even know what the conductor is, so it doesn't conduct half as well as a conductor. Has less resistance than a conductor? No, if it had less resistance than a conductor, it would be a better conductor than a conductor, and it isn't. Has more resistance than an insulator? No, insulators have the most resistance. So A is the correct answer. Well, there you go. Thank you for listening to this tutorial. I'll see you back in the next one. Don't be too worried about Ohm's law. The Ohm's law triangle is a good thing to get used to, and we'll be talking more about Ohm's law and other things in tutorials to come. Cheers for now. Thanks for listening. This is Ron, VK2DQ.